In this video, I'm going to do a couple of examples of finding the area enclosed by two curves. So in the first example, let's take the curves y equals 2x and y is equal to 6x squared. Well, the first thing that we want to do is we want to graph these. Now, you can graph them any way that you want. Again, in this class, I generally like to use Desmos. So I've already graphed these two curves in Desmos. That would be just here's y equals 2x, of course, is a straight line. So that would be this red line. And y equals 6x squared is a parabola. And so this blue curve is that parabola. And so we're looking for the area that is bounded by those two curves or enclosed by those two curves. So we can see that the area bounded by them starts at this point right here at 0, 0, and goes up to this point right here, which is 0.333. I'm going to use that as a fraction, 1/3. And so that's what we really need are the x values. So the bounds on the x-axis are from x equals 0 to x equals 1/3. So of course you could do this algebraically if you were so inclined to do that. You could simply take 6x squared and set it equal to 2x because we want to find algebraically where these two curves or these two functions are equal to each other. In other words, where they cross. So to do the old-fashioned factoring method, I would simply subtract 2x to the left-hand side, set that equal to 0. I can then factor out a 2x, leaving me with 3x minus 1 equals 0. Then we want to take each factor and set it equal to 0. And when we do that, we end up with x equals 0 and x equals 1/3, which is exactly what we had found by looking at the Desmos graph. So the other thing that we need to get from our graph, and I like to make a little sketch of the graph. I would encourage you to do that, is just to make a little sketch. If you need to, you can go back to take a look at this. Okay, so it looks like the line was on top. And so we're going to have something that looks something like this. This doesn't need to be super accurate, just something to give you an idea as to what was going on here. And so this one's going like that. And so our points of intersection right here, this of course is at 1/3. And this point right here was at 0. And we're looking for all of this area in between these two curves. Now, the one important thing that we need to know here is which curve is on top. So the linear curve is on top. So when we set up our integration problem, the area is going to be the integral from 0 to 1/3. That's the area that we're integrating over. And we want the linear curve to be the top function, my f of x, minus my g of x, which would be the 6x squared. And so this is our integration problem. Half the battle with doing any type of an integration application, including area between two curves, is setting up your initial integration problem correctly. When I grade exams, the first thing that I look for is, did the student set up the integration problem correctly? And so this is what I would be looking for. Are the bounds of integration correct? Do you have the top function, the function on top, above the one on the bottom? So do we have that? Yes, we do. We have 2x minus the 6x squared. The next thing to do is to simply go through and do the integration. So this is a relatively straightforward integration problem. We're going to have 2x squared over 2 minus 6x cubed over 3 evaluated from 0 to 1/3. This, of course, simplifies a little bit. We can cancel out those, so we have x squared, and of course 3 goes into 6 2 times, minus 2x cubed evaluated from 1 to 0. And so now we just have to do fundamental theorem of calculus. And so, whoops, I didn't mean to put 1 there, I meant 1/3. So we're going to have 1/3 squared minus 2 times 1/3 cubed. There's my f of b, minus my f of a, which is going to be all just 0 minus 0. Okay, give myself a little more room there. Well, 1/3 squared is going to be 1/9 minus 1/3 cubed is 1/27. So that would be times 2 is 2/27. And 1/9 is equal to 3/27 minus 2/27 is going to be 1/27. So my final answer is the area is 1/27. So the purpose of this video is to just give you another example of how to set up a basic area between two curve problems. There was nothing particularly challenging about this. It was relatively straightforward. It was easy to find the points of intersection of the two graphs. Sometimes that's a little bit more complicated. Let's just do one more. All right, so now let's find the area between x plus y squared equals 6 and x plus y equals 0. Now, the first thing to notice about this is that neither one of these equations is solved for x or solved for y. Neither one of them is explicitly defined as a function of x or a function of y, which leads me to believe that I need to determine whether I want this to be a function of x or a function of y. So before I even consider that, let's go back to Desmos. Let's graph these. And so now let's take a look at these two graphs. Oh. And there we go. Well, it would appear that I have a sideways parabola. And so the bounds of integration are going from this point right here to this point right here. But if we were to do this, if we were to set up the bounds of integration along the x-axis, then what we would be doing is we would be going from x equals -3 to x equals 2. But we would have to set this up so that this function, the parabola, is on top of the line. And that's going to be problematic when we get over here, because this parabola extends way over here beyond that point of integration. So this is a problem that I call a sideways problem. This is going to be much easier to set up so that we are looking at these equations where x is a function of y. So let's go back to the whiteboard. If x is going to be a function of y, I would rewrite this as x is equal to 6 minus y squared, and x equals -y. Now, let's just graph these. We know that one was a sideways parabola, looked something like that. And if we go back to Desmos, we saw that the other one is going to be doing something like this. All right. And there's our points of intersection. I'm still getting used to using this pen on my sketching tablet, so my graphs aren't that great. So now, the way that I look at it is, let's go to a different color. Let's use green here. So what I'm doing is I'm setting this up sideways. So I'm actually making little sideways rectangles. If you have read my notes and you understand the basic concept of how we develop the area between two curves using Riemann sums, you know that what we're really doing is we're creating a whole bunch of little rectangles. Well, my rectangles are sideways rectangles. And so the top of this rectangle is right here, and the bottom of the rectangle is right here. That means this is the upper function, and this down here is the lower function. So when we set up the integral, we're going to be setting up the integral so that the parabola is on top. 6 minus y squared minus, and let's be careful with the parentheses, minus the other equation, negative y. Now, the only other thing we need to do is find out the bounds of integration, but we want to find the bounds of integration along the y-axis. Okay, the bounds of integration are going to be along the y-axis. This would be my a, and this would be my b, okay, along the y-axis. So we can go back to Desmos, take a look at what we had there, and the y values there were 3 and negative 2. So we are going to set this up so that the bounds of integration area is going from 3 to negative 2. And of course, this is 6 minus y squared plus y dy. We are integrating with respect to y now. All right, so let's just go ahead and integrate it. This is a straightforward integration. We're going to have 6y minus 1/3 y cubed plus 1/2 y squared, evaluated from 3 to negative 2. Well, this is where we simply get into a lot of arithmetic now, so we got to be real careful with our arithmetic. So, area is going to be equal to 6 times 3 minus 1/3 times 3 cubed plus 1/2 times 3 squared minus 6 times negative 2 minus 1/3 times negative 2, and that would be cubed, plus 1/2 times negative, or times, yeah, negative 2 squared. Now, you can also do this in Desmos. You can just set up your antiderivative right here, put that into Desmos, and then just evaluate these two functions at these two different values, and it would be very, very simple. But I'm just going through the mechanics of what you're actually doing here. And so it looks like once you go through and you do all of the arithmetic, and I'll let you do that on your own, we end up with 125 over 2. That's 125 over 2. Actually, I'm sorry, over 6. I can't read my own writing here. I've got the solution already done. Well, this gives me a chance to use the pen here. Oh, there we go. So it's 125 over 6. And there is the area between these two curves. So what we have just found is, and let's go to a highlighter here. We have just found all of this area in here. Now, one of the challenges to doing any of these problems is determining whether you want to write your functions as y in terms of a function of x or x in terms of a function of y. And you'll see in some problems it doesn't matter which way you do it. In some cases you can do it either way, but it'll be easier one way than it would be the other way. In this particular problem, we had to do this where x is a function of y and then integrate along the y-axis, and with the bounds of integration being along the y-axis. All right, I think that's it for this video.